In this video I am going to discuss about two very important theorems related to separability. But before going through those two theorems, proof of those two theorems in fact, we need to consider few definitions initially. So here you can see I have given the heading separable space. This is a very important part for topology, especially it is very important for 6th semester students. So you can see in the first part I have given the definition of separable space. Now obviously I have written all these definitions in terms of a metric space. Now you can write the same thing in case of a topological space, but in that case you have to change this x comma d by writing it x comma tau. That means here I have written a metric space x comma d is said to be separable. Instead of a metric space, if you want to write it in terms of a topological space, simply replace x comma d by x comma tau. Throughout this convention should be followed. Now here, what is the meaning of a separable space? Initially you are going to consider a metric space x comma d, which is termed as a separable space, provided this particular space x should contain a countable dense subset. Now obviously what does it mean? Whenever you are considering a certain subset, obviously that is non-empty countable, say that is A, which is a subset of X, and if it is dense means you have to find out the closure of A, and if you can show that A bar is equal to X, that is closure of A is equal to X, then only you can say it will behave like a dense subset. So already you have said it is a countable dense subset, that means A is countable and also it should satisfy the condition A bar is equal to X. So this is the criteria of getting a separable space. Now then there is a huge confusion in most of us that what is the meaning of local base, and simply whenever we are considering the base corresponding to an open set. So that's why I have given these two notes. In the first note I have defined what is the meaning of local base. In the second note I have given whenever you want to consider a family of open subsets, how can you define a base. So here you can see x comma d is as usual a metric space. Let us consider a family of all possible neighborhoods corresponding to any point arbitrarily chosen. Obviously small x belongs to capital X. Now here you can see I am going to choose a point arbitrarily. Just remember this point, nothing else. Also try to obtain a certain subfamily of this collection, or better to say of this family of neighborhoods, say that is given by capital Bx or script Bx, whatever. Then this particular structure or subfamily will be considered as a base corresponding to this capital Nx if for every member n is a part of Nx, if you can show there exists a part or a specific expression b which is a part of script Bx or capital Bx satisfying the criteria b is a subset of n. Now obviously this entire situation is occurring on the basis of the point x, so that's why you can say you can consider this script Bx is nothing but the local base about the point x or at the point x. Again I am saying the definition. Initially you are considering a family of all possible neighborhoods corresponding to the point small x belonging to capital X. This is first part. Then you need to consider a family, better to say a subfamily. Obviously you need not to consider all possible structures of Nx, a certain part of it you can consider. So that certain subpart is considered as a subfamily, that is script Bx. Then it will be considered as a base. Base for which one? Base for the original one, that is Nx. Correspondingly the condition is what? For every member of Nx you must have a member of Bx, such that if you say the member of Nx is capital N, if you say the member of Bx is capital B, then B must be a subset of N. And because you have defined everything on the basis of this point X, so you can say it is nothing but a local base corresponding to the point X. Now in note 2, just there is certain change, and what is that? Here you can see instead of a point, initially I would like to say let us consider a family of all open subsets of a metric space x comma d. That means this family is considered as xi. Now here you can easily understand the difference. Here I have taken a point, then I have considered all possible neighborhoods, family of all neighborhoods, but here I have considered all possible open subsets. Okay, so previously it was neighborhood, now you are considering all possible open subsets. This is the main difference. Now within this family you can consider a subfamily, say that is given by eta. Then this particular subfamily will be considered as a base corresponding to any arbitrary point small x belongs to capital X. If it is possible to find out a suitable neighborhood n of x, Correspondingly, you can find out a suitable member B of xi satisfying this condition, that is x belongs to B, which is a subset of n. Previous definition entirely depends on this point x, but in the second case, initially you have to find out the family of open subsets. After that, you have to create the subfamily, then you can choose the point. Whereas the previous note, you can see the point should be defined initially. So in case of local base, you can remember, or you can realize that thing, the point is very very important. That's why the term local is implemented. And in case of base, it is not necessary that you have to choose the point. You can initially consider a family of all open subsets. Okay, so just remember these two basic differences. Now here we have another two important definition. First definition is what? First countable space, and the second definition you will see it will deal with the definition of second countable space. Now whenever you are considering a metric space x comma d, it will be said that it will satisfy that first axiom of countability, or simply you can say it is a first countable space, provided for any point small x belonging to capital X, it should contain a countable local base. I hope it is clear to us what is the meaning of local base, what I have discussed in note 1. And then if for every point belonging to x, if you can show that there exists a countable local base corresponding to that point, then it will be considered as first countable space. That means first countable space simply implies for every point you must have a countable local base. That's it. This is the main criteria. And again I will say, if you want to write the same definition in case of any topological space, simply change x comma d by x comma tau. Tau is the topology induced on x, and here d is the metric induced on capital X. Now moving on to the second definition, you will see I have given the definition of second countable space. Here also you can see I have written in the similar manner that a metric space x comma d will be considered to satisfy the second axiom of countability if there exists a countable local base for xi, where xi denotes the family of all open subsets of x. That means it depends on the definition of second countability, second countable space. Okay, that means initially we have already created in the first definition what is the meaning of local base. Just implement the definition of local base, you will get the idea of first countable space. Whenever you are using the definition of base, not local base, I will say, then you will get the idea of second countable space. So that's why here xi denotes the family of all possible open subsets of x. So these two definitions you have to remember, otherwise it is impossible for you to understand the following theorems. Now in terms of your examination point of view, these two theorems, two consecutive theorems will be discussed in this video. You will find both these theorems are extremely important for your examination. Now also those who are preparing for different competitive exam, also you have to know the basic difference between first countable and second countable space. So I hope you can understand from this particular video in the first page whatever I have discussed. So without wasting any more time, let us consider the first theorem. Every metric space is separable. Very very important. So you can start like this: x comma d be any arbitrary metric space, small x belongs to capital X, this is an arbitrary element. These are formal statements, I know you can easily understand all these things. We have to show capital X, that is the metric space under consideration, is first countable. So just remember the definition of first countability. If you can show for every point x belonging to capital X there exists a countable local base, then your result will be proved. So that's why I have written it is sufficient to show that there exists a countable local base for every x belonging to capital X. Now let us consider the collection of all possible open balls or open spheres having center at x. You can see I have given the structure like this. You are considering the open spheres whose center is at x with radius 1 by n. Now one thing you can easily understand, if you gradually increase the value of n, this particular radius will be diminished. That means if you put n equals to 1, 2, 3, 4 and so on, in this way you can enlarge this value of n. Then gradually a situation will arise when n is very very large, and consequently this will be reduced to or tending towards what? 0. So this family is denoted by script bx or capital Bx, whatever you say. Now we claim that this particular collection will ultimately form a countable local base, and the necessary condition is that correspondingly you have to consider a certain open set, say G, and there exists a neighborhood, say capital N of x, then obviously by the definition of open set you can say x is a member of what, G. Definitely it should be contained by N. That means you are considering every point x that must behave like an interior point of G, and we are choosing this neighborhood in such a way that it will also contain the original open set under consideration G and obviously the point. Now G is open, so each and every point is an interior point as I have mentioned earlier, so you can create an open ball. Obviously for that you have chosen epsilon greater than 0 arbitrarily small, so the open ball can be written in this way, Sx comma epsilon. So here you can imagine that the original open ball is what, Sx comma epsilon, which is contained within what, G, which is further contained within N as per our construction. This is capital N. Now if we choose N very large, then obviously you can understand 1 by N is tending towards 0, so that you can say as epsilon is tending towards 0 and it is positive, so 1 by N must be less than epsilon, and hence you can say S of x comma 1 by N should be a subset of S of x comma epsilon. Obviously you are choosing N is very large, which is further a subset of G, which is further contained in N. So technically right now you can say every neighborhood of x contains at least one member of G, because this is that particular member which is further contained in G. That means you are choosing a certain point, say that point is x, which is contained within this open ball, which is further contained within this open ball, which is further contained in G. So technically for every possible point x, you can say you have created a countable local base, and this collection is already mentioned by means of capital Bx, so hence you can say this Bx as per our claim definitely forms a countable local base at the point x, and hence you can say because x is arbitrary, so the space x comma d is definitely first countable. That means every metric space must behave like what, first countable space. Now here you can understand separability. Now every metric space is separable. Again I will show you the definition. If you consider the definition, what does it mean? A metric space is separable if it contains a countable dense subset. So here we have proved the structure is definitely what, countable, and obviously it will satisfy the basic criteria of existence of local base. So from this particular aspect we can say definitely every metric space is nothing but a separable space. I haven't written that one, but I hope you can understand this one. If you have any question, you can put it your question in the comment box section. Now we have a very important result, another important result rather I will say, that is a metric space is separable if and only if it is second countable. Now here you can see x comma d is a separable space. As usual we can consider in this way, and we define a certain set A which is collection of the points like xn. So practically if we assume that A is nothing but a countable dense subset of x, then as per definition we must have A bar is equals to x. Now remember this condition because later on we have to use this one. Now for our convenience, let us consider a certain collection that is given by capital B, which is given by the collection, or which is nothing but the collection of all open balls having center at xn with certain radius 1 by m. Obviously n and m are integers, or better to say positive integers or natural numbers. So as per our condition, if we can show that this particular collection is behaving like a countable dense set for some family G of all possible open subsets of X, then our result will be justified. Now definitely B is considering different values of M and N. Obviously technically it will consider infinitely many elements, so we can say B is a countable family of open countable subsets, and hence because it is a collection of open countable subsets, so definitely itself it is countable. Now every possible open ball is also nothing but an open set. Now I hope you remember already in metric space theory you have studied about this theorem that every open sphere is an open set. That's why I mentioned this one, and every open ball or open sphere is also an open set. So technically whatever the member of B each of them is behaving like an open set. So if we can justify that this collection B is behaving like a base for G, then our result will be proved. And also must not forget what is G. G is the collection of all possible open subsets of X. Now let us take any point X belonging to G arbitrarily. Epsilon greater than 0, you can choose in an arbitrary fashion, or you can say epsilon greater than 0 be given sufficiently small so that epsilon neighborhood of X, or better to say you can create a certain open ball that must be contained within G. Now here I have written we choose a positive integer m naught greater than 2 by epsilon. You need not to write this one initially, later we can define how we have to choose this particular expression. So just forget this one right now, later on we can explain how to consider this one. Already a bar is equal to X, because already we have assumed A is countable 10 subset of X, so a bar is equal to X. Now a bar, what is the meaning of a bar? A bar is nothing but closure of A. Closure is nothing but the collection of all adherent points. So you can say every point of X is behaving like an adherent point of A, because this is the condition by means of which we can state this one. Also I have given the sub note here that by definition of closure of a set, it is the set of all possible adherent points corresponding to the original set. So it is the collection of all adherent points. Adherent point means what? You can consider any limit point as well as you can consider any isolated point. Now as per our construction, we can say there must be some open sphere whose center is located at X and it should contain some point of A. So say that open sphere can be taken in this form, 1 by m naught. Obviously as per our construction it should contain some point of A. Say that point is xi. So xi is a member of this. Use the concept of metric space. So distance between x and xi must be less than 1 by m naught, and hence you can say x is a member of S of xi comma 1 by m naught. That means x is also a part of this open sphere having center at xi with 1 by m naught as radius. Now if this part is true, just remember this one, already we have defined m naught greater than 2 by epsilon, and I also say initially you need not to memorize this one, later on automatically it will be defined. Okay, now you will see how to define this one. Now anyhow we have to prove this particular open ball is contained within S of x comma epsilon. So we can use the famous triangle inequality, but before that we need to consider a certain element present in this open ball. Say that element is y. So if you consider there exists some y, or this particular open set is containing y, then what can you say? Distance between y and xi must be less than 1 by m naught. Actually we are using the definition of open set, nothing else. Now using triangle inequality you can see distance between x and y must be less than distance between x comma xi and plus distance between xi comma y. As per your construction you can say this part is less than 1 by m naught, this part is also less than 1 by m naught as we have proved earlier. So you have obtained 2 by m naught. Now I hope you can remember, as I mentioned earlier, why we have chosen this particular quantity is less than epsilon. Again, if you can't remember, then recall the basic structure. What was the basic structure? Here I have considered m naught greater than 2 by epsilon. So technically m naught epsilon is greater than 2, or epsilon must be greater than 2 by m naught. So here the situation arises in such a way that you have obtained 2 by m naught type of structure, as you can see here, 2 by m naught. So this part must be less than epsilon. So distance between x and y is less than epsilon, and hence you can say y is a part of S of x comma epsilon. So technically y is any arbitrary element, so you have taken that one from this open ball. Ultimately you have shown it is a part of S of x comma epsilon, and hence you have this particular definition. That means this open ball must be contained within S of x comma epsilon. Now you can select any arbitrary point x present in this structure. So technically it is part of S of x comma epsilon, which is again contained in G. So every point like x taken from G is definitely a member of what? S of xi comma 1 by m naught. But actually it is a part of what? B, our collection. That means it will contain the point x and itself contained within G. So this is ultimately showing the fact that this collection B must behave like a base corresponding to the set G, and hence you can say x comma d is nothing but a second countable space. So this is the first half. Now if you want to prove the second part, then what you have to do, you can start like this. Conversely, you have to show that x comma d is a second countable metric space, and we have to show x comma d is also separable. Now here initially by definition we have assigned a suitable countable base that is given by beta. You can say any other thing, nothing special in it. And also we have created the collection capital B, which contains the elements of the form Bn. Obviously you can understand, for different values of n you will get different B. That means for n equals to 1 you will get what? N is equals to 1 means you will get ultimately this particular structure will be nothing but B1, and obviously n equals to 2 you will get B2. So for different values of n you will get small b1, small b2, small b3, which are selected from capital B1, capital B2 and so on respectively. So that's why I have said we select a point small bn is a part of capital Bn. Now here how many elements you can select? Obviously infinitely many structures can be taken like this. So this collection is countable, and now if we can show that this is dense in X, then our result will be complete, or proof will be complete. So for that purpose, let X belongs to X, G is an open neighborhood of X. Now here you are considering second countable metric space, that's why I am not using the term local base. Okay, so you can see I have chosen a certain member Bn not belonging to this collection, such that it will contain the point X and itself contained in G, but Bn not belongs to B. Obviously it will ultimately shows you the fact this small bn naught is a part of capital Bn naught. Why? Because small bn is a part of capital Bn, which is further contained within G. That means you can say G contains a point obviously of particular set B. That means G is also an open neighborhood of X. That means every possible neighborhood of X must contain a point of B as per our construction. And finally you can say, thus you can say X is behaving like an adherent point of B, and if it is an adherent point, so definitely it is a part of the closure of B, so X belongs to B bar. And hence you can say initially you have selected small x from capital X, now you have shown small x is a part of B bar. That means capital X is a part of or subset of B bar. But everything is contained in original metric space or topological space, whatever you say. So B bar is also a subset of X, and hence combining these two you will get B bar must be equal to X. That means you have obtained this particular collection capital B is nothing but a countable dense subset of X, and that means X comma D must be separable. Now again I will return to the first theorem. Whatever we have proved earlier, you can see actually here I have written every metric space is separable. You need not to show this one. Every metric space is separable. If you want to prove this one, you have to write many more things, but as per your examination point of view, you have to show every metric space is first countable. So I am excluding this term and simply I am writing every metric space is first countable. That's why I have proved this one, X comma D is first countable. And again I will let you remember that whenever you want to consider in topological space, then simply you have to write x comma tau instead of x comma d. Just remember this thing. So the basic idea is to define the separable space. Then what is the meaning of first countable, second countable space? You must not forget what is the criteria of local base and base. Local base always implemented by means of a point, whereas whenever you are considering base, you need to consider the family or collection of open subsets of original space capital X. Okay, and here in this theorem again I will say simply remember the criteria, every metric space is first countable. You need not to show that every metric space is separable. In fact, there are several exceptions whenever you cannot prove it, and that's why simply first countability for every metric space is important. But in the second case we have shown every metric space is separable whenever it is second countable, and vice versa. So I hope this video will be useful for your examination, and obviously you can prepare all these theorems and all these notes properly, so that if it comes in your examination you can do it properly. Thanks for watching, and if any question is there you can ask me in the comment section. Thank you.